Hello and welcome back to Machine Learning. I'm Jovita Christie, and in this video, we are going to talk about generative adversarial networks. And then we're going to talk about adversarial attacks, which are attacks that can be made on neural networks. So not just neural networks, but any machine learning model. So let's begin. First of all, to understand GANs, we first have to understand what is discriminative modeling and what is generative modeling. So in supervised learning, we may be interested in developing a model to predict a class label given an example of input variables, right? So supervised learning can be used for prediction, and in particular, it can also be used for classification, predicting classes. And this predictive modeling, we know it is called classification. And classification is also traditionally referred to as discriminative modeling. Okay, so classification is nothing but discriminative modeling, because what happens is the model has to discriminate between the inputs that are received and decide which input belongs to which class. So that's why classification is discriminative modeling. Alternately, if you use supervised models that summarize the distribution of input variables, they are used to create or generate new examples in the input distribution. So we know that unsupervised models, they find the interesting patterns within the data. And so they can be used to, find out what is the probability distribution of that data. And if it is known that this is the distribution, then you could use such a model to even generate new data. Okay. So these types of models that can generate new inputs based on whatever is the distribution of the input given they are known as generative models. So for example, you may have a single variable, okay, and you may know what is its distribution. For example, it could have a Gaussian distribution, which is also known as a normal distribution with a bell shape, right? It's very common and very easy to recognize because of the bell-shaped graph. So a generative model may be able to sufficiently summarize this data distribution and then be used to generate new variables that plausibly fit into the distribution of the input variable. Okay, so once you know that the data you have is a normal distribution data or normally distributed, you might be able to generate new data that can, fit into this kind of a distribution with the other data. So a really good example of a generative model would be one where it's able to generate new examples that are not just plausible in the sense possible, okay, but also indistinguishable from real examples from the problem domain. So indistinguishable means you can't tell that this particular example or input is actually generated by the model instead of being, already present in the data set. So that's what generative modeling is. Now let's take some examples of generative models. So a very good example of this is the naive Bayes algorithm, which we have studied very extensively in the previous videos. It is a generative model, but it is being used as a discriminative model because we know that naive Bayes is also used for classification. So naive Bayes is actually can be used for generation also, but it is being used for discrimination. So for example, we know how naive Bayes works, right? If you have 4 classes and you have some input data, it is going to tell you what is the probability that that input data belongs to class 1 or class 2 or class 3. So it gives you probabilities of that input belonging to each and every class. So in general, it provides you or a sort of a summary of the probability distribution of each variable, input variable. So when a prediction is made, the probability of each possible outcome is calculated for each variable, and then those probabilities are combined and you will check which is the most likely outcome based on the highest probability. But you could reverse this, okay? You could reverse this naive Bayes algorithm in such a way that the probability distributions of each variable can be sampled to generate new plausible or independent feature values. Okay, so you could indeed reverse the algorithm so that you're not calculating probabilities anymore, but you're trying to generate inputs which are matching the distribution of the other inputs present in the data set. Now let's move on towards what are GANs. So a GAN, which is a generative adversarial network, it has two submodels. One is the generator model. It generates new plausible examples from the problem domain. So if you provide a data set, the first model of GAN, which is the generator model, is going to try to generate more samples just like the samples that are present in the data set. Okay, it's going to try to generate new samples based on what it sees. And there's a second model, which is the discriminator model, which is going to be used to check if those samples are, if a certain input is a real input, that means which is actually taken from the data set, or is it fake, which means it was generated by the generator model. Okay, so the discriminator is only going to do a binary classification. And the idea behind that is that you want the generator model to actually be able to fool the discriminator into thinking that the examples generated by it are belonging to the domain or the data set. Let's talk in detail about the generator model. So the generator model takes a fixed length random vector as an input, and then it generates a sample in the domain, okay? And this vector is randomly drawn from a Gaussian distribution, and it is used to seed the generative process. Now, once the training is done, then the points in this multi-dimensional vector space will start corresponding to the points in the problem domain, and it will form a compressed distribution or representation of the data distribution. And then this vector space that you have is referred to as a latent space or a vector space comprised of latent variables. So these are variables that you cannot see. Okay, latent variables are also known as hidden variables, which are important for that particular domain, but are not generally observable, not variables that you can see directly. Okay, and once you finish training, then the generator model is kept and it is used to generate new samples. So once the training is over, the generator model is going to be able to generate new samples. So this could help you a lot if you had a very small data set and you wanted more examples, more samples, then you could use this to generate more samples. Next, we have the discriminator model. So this kind of model takes an example from the domain as an input, okay, which is now this example could be either real or generated, and then it's going to predict a binary class label of real or fake. Okay, so it's going to predict whether that particular example is a real example or it's a fake example which was generated by the generator model. Now, this real example comes from the training data set, and the generated examples are output which are generated by the generator model. And the discriminator is a normal classification model. So it's just a classification model dividing things into real and fake. And once the training process is over for the GAN, you will discard the discriminator model because you don't need it anymore. We are interested more in the generator model that's going to generate new samples for us. So GANs work as a two-player game, and I'll tell you how. Because whenever the discriminator successfully identifies, that this is a real sample, this is a fake sample, then it is rewarded, okay? It is rewarded in the sense no changes are needed in its parameters because it's doing the work that it has to do. But on the other hand, the generator is penalized. Okay, it's penalized because um, it was not able to fool the discriminator. And that's why you require large updates to be made to the model parameters of the generator. So that's why it's a two-player game. Um, so alternatively, what happens alternately, the generator, if it manages to fool the discriminator, then it is rewarded because then no change is required to its parameters. But the discriminator is penalized and it has to, be updated. The parameters have to be updated. So that's why GAN is a sort of a two-player game where if one player is winning, the other's losing. And if the other one's winning, the other one's losing, then this one's winning. So that's why it is a two-player game. This is a kind of a simple, very simple architecture of GAN. So there's a random input vector, which is fed to the generator model, which is going to generate an example. There will also be real examples from the data set itself, and both will be given to the discriminator. The discriminator will have to find out if this is real or fake. So it's a binary classification. Based on this result, you will update the discriminator, you will update the generator model as well. Now let's take a look at some areas where GANs can be applied. So one of the major advancements in the use of deep learning methods in domains is in domains like computer vision, and in that there is something called data augmentation. So what is that? It results in better performing models, both increasing model skill and providing a regularizing effect, reducing the generalization error. Okay, so data augmentation is about, adding data to images. Okay, so you are creating new artificial plausible examples from the input domain in which the model is trained. So it means you are able to create images or you're able to add something to already created images. Also in complex domains where you have limited amount of data, you could use a GAN to generate more data. Okay. And GANs have also seen a lot of success in domains such as deep reinforcement learning, which we are going to see in our next video. And GANs have also been able to model high dimensional data and provide also handle missing data. Okay, because if data is missing, this one could just generate data in its place. If it's high dimensional data, GAN can even model that. It can also provide multimodal outputs. So multimodal outputs would be like outputs which are generated in different modes, like maybe text or speech or gestures. Okay, it can also provide multiple plausible answers. So if you ask a question, it could probably give you 5 possible answers. It could generate 5 possible answers for that question. Okay, it is also able to generate photos, which are so realistic sometimes that even human beings are not able to tell whether they are real or fake. Okay. Now, what else can GANs do? So GANs can also do image super resolution, which means it could convert a low quality, low resolution image into a high quality image. Okay. It could also create art, which means it could create, paintings, sketches of people, stuff like that. It could also do image to image translation. So for example, it could convert an image that was taken at night and, make it look as if it was taken during daytime. It could convert a summer image into a winter image. So it could do things like that. Now let's move on to adversarial machine learning. So what is adversarial machine learning? It is a machine learning technique that attempts to fool models by supplying deceptive input. Okay? And the most common reason to do this is to cause the machine learning model to malfunction, because you're trying to provide an input that's going to create some sort of an issue with the machine learning model. So it can cause this model to malfunction. And most machine learning techniques were designed to work on specific problem sets in which the training and test data are generated from the same statistical distribution, right? So IIDs are nothing but independent and identically distributed variables. So that's how machine learning techniques work. They work with IIDs. But then when those models are applied to the real world, then these adversaries could supply some data that would not fit into this statistical assumption that all of this data belongs to the same statistical distribution. And when you do that, then this data could be, then this kind of data could actually exploit this machine learning model and even compromise the results. So let's take a look at some examples of what adversarial attacks could look like. So the first one is spam filtering. So often spam filtering is done on the basis of some words that are present in the email. And what people could do is to have an adversarial attack is to misspell the bad words or insert good words instead of bad words. So usually, like, if there are words like lottery, then such an email would most likely go to the spam folder. But instead of using the word lottery, they might, just replace it with some other word that will not, cause that email to be filtered as spam, or they might just misspell the word lottery, and that could also do the trick. So this is a type of an adversarial attack. There could be attacks on computer security, okay, such as sending some malware code within a network packet, or some misleading signature detection. All this could cause some problem with the computer security. Also, there could be attacks on biometric recognition, right? Biometric is where people are recognized on the basis of their eyes or basis of their fingerprints or face, okay? And here also some of the biometric traits could be faked, and it could be made, you could exploit or impersonate a legitimate user. You could also compromise users' template galleries, okay, that adapt to updated traits over time, right? So even that could be done. And researchers showed that by changing only just one pixel within an image, it's possible to fool deep learning algorithms by just changing one pixel. And others 3D printed a toy turtle with a texture engineered to make Google's object detection AI classify it as a rifle, regardless of the angle from which the turtle was viewed. So there was this experiment done where some people printed a 3D printed a toy turtle, and the texture of the toy turtle was such that Google's object detection AI was classifying it as a rifle, no matter which angle it took a picture of this turtle from. Okay, so the texture of a turtle is completely different than that of a rifle. So even though the object was a toy turtle, its color or texture was of a rifle. And so Google's object detection AI was fooled by it and classified it as a rifle. And creating this kind of a turtle only required a low-cost, commercially available 3D printing technology. Also, a machine-tweaked image of a dog was shown to look like a cat to both computers as well as humans. And a 2019 study reported that humans can guess how machines will classify adversarial images, and because of that, they are able to find out ways to fool machines. For example, there was an autonomous vehicle, which means something like a self-driving car, and there was a sign which said a stop sign, so you're supposed to stop there on the road, but instead that sign was made to look like a merge or a speed limit sign, because of which the autonomous vehicle did not stop. Okay, so that's how adversarial attacks can be done. Also, McAfee, which is a popular antivirus system, attacked Tesla's former Mobileye system, and it fooled it into driving 50 miles per hour over the speed limit by just adding a 2-inch strip of black tape to a speed limit sign. So even this is possible. And also there are adversarial patterns on glasses or clothing designed to deceive facial recognition systems or license plate readers. They have all led to stealing of such kind of objects. Also, an adversarial attack on a neural network could allow an attacker to inject algorithms into the target system. So algorithms which are not required, not present, those kinds of algorithms can be injected. And also researchers can now create adversarial audio inputs to disguise commands so that some intelligent assistants might malfunction because of that. Clustering algorithms are also used in security applications, and malware and computer virus analysis aims to identify malware families and to generate specific detection signatures. Now let's talk about some attack strategies. So there are several attack strategies to do an adversarial attack. Number one is evasion. Evasion attacks are the most prevalent types of attacks right now. For instance, spammers and hackers often attempt to evade detection by obfuscating the content of spam emails and malware, which we just saw spamming. Samples could be modified in such a way that they would evade detection and would be classified as legitimate, even though they are not. So it does not involve influence over the training data, okay, but it tries to modify the emails that are sent in case of spamming. And a clear example of this is an image-based spam in which the spam content is embedded within an attached image to evade textual analysis by anti-spam filters. So this is a very good way to do it, that instead of actually typing the words, you could just take a screenshot of, type them somewhere else, like in Notepad, and then take a screenshot and paste the image in the email. So because the spam filter is used to analyzing words, it's not going to analyze the image, and it's just going to let that image pass as a normal email. And another example is given by spoofing attacks against biometric verification systems. Another attack strategy is poisoning. So poisoning is adversarial contamination of the training data itself. And we know that machine learning systems use training data to get trained, and then they can be used properly. So machine learning systems can be retrained using data that are collected during operations. Like intrusion detection systems are often retrained using such kind of data. And so your attacker might poison that kind of data by putting some malicious samples into it during operation, which could, disrupt the training eventually. And the final strategy is model stealing. So in model stealing, which is also sometimes called model extraction, an adversary probing a black box machine learning system in order to either reconstruct the model or extract the data it was trained on. Okay. So this is all about, there's a trained model and you want that model for yourself. So you're trying to get that, or you're trying to get the data that it was trained on illegally. And so this can cause issues when either the training data or the model itself could be, sensitive or confidential. So for example, model stealing could be used to extract a proprietary stock trading model, right? Which the adversary can then use to their own financial benefit. So it's a stock trading model which predicts what will be the prices of stocks, but it's proprietary, it's not free, and someone could just steal it and use it for their own benefit. So these are some of the attack strategies. I hope you understood this, and I'll be back with the next video. So I'll see you there, and thank you for watching.